Hello again. This video lecture 22.3, is going to be discussing a section in chapter 22, in fact, section 4, which is titled as the electric field due to a line of charge. So what we're talking about in this section is our first situation in which we deviate from just point particle, 1 or 2 or 3 or 4 point particles, but instead have something where the charge is smeared out over an extended body. And in this case, it's basically a one-dimensional body. It could be over a straight line, like something shaped like this pen or pencil, with charge smeared out along it, almost like paint. Or it could be a curved line. You can have curved lines. You could have something shaped like a circle, with charge smeared out around the circumference of the circle. We would call that a ring. And in fact, that's the first situation we're going to deal with in this section. But the general idea here, the key idea that this section is introducing us to, is the procedure for calculating the electrostatic field that is caused by what is called a continuous charge distribution. That means charge smeared out over a shape of something that isn't a particle, like this pencil. Okay? If we have charge smeared out along this length of this pencil, and then we're sitting at a point near that pencil and want to know the electric field created at this point where my fingertip is from the charge on this pencil, I can't treat the pencil as a charged particle because it's distributed in shape. It's not a point particle. So how do we find the electric field created by a distributed shaped object with charge? That's what this whole section is about. Now, a little bit of a heads up. It takes a little getting used to how to do it. But what it ultimately relies upon is the ingenuity of calculus, as you will see, and treating something extended as being an infinite number of little infinitesimal pieces. That's the beauty of calculus. I'll show you how we use that idea. But let's be clear what we're going to start with so that we know exactly what we want to do. We're going to take an object that's a circle or a ring, okay? And it's drawn in this picture as a blue circle. And any ring or circle has some radius. That's denoted here with capital R. And we're going to take some total amount of charge, we'll just call that little q, and we're going to smear that out, almost like paint, and smear it out evenly, that's important, around the circumference of that ring. Okay? Total charge q smeared out evenly around the circumference of that ring. Again, the ring has some radius, big R. And we're going to want to find the electric field created by this charge distribution. Now, to make it a little bit manageable, we're going to pick a special place or a special axis to calculate this electric field for. Notice the ring is in the xy plane with its center at the origin. We're going to pick then a point P that's on the z-axis. The z-axis goes through the center of the ring and is perpendicular to the xy plane. And we're going to pick a point P, it's just a point, there's no actual charge up there, that's on the z-axis at coordinate z. If you like, that's the distance of point P from the origin. We want to know the electric field at that point P, created by that charged ring. Now, one of the things that's going to be handy to think about when we do this is a quantity for a line type distribution, something called the linear charge density of the ring. Linear charge density, charge per unit length. And therefore the SI unit would be Coulomb per meter. Okay? That's the unit for linear charge density. The symbol for a linear charge density is a lowercase Greek letter lambda. And if you have a linear charge distribution, like this ring, where the total charge of some amount, in this case Q, is smeared out uniformly, evenly over the length, then the linear charge density lambda is the total charge over the total length, if it's spread out uniformly. So the linear charge density lambda for this ring is the total charge of the ring Q over its total length, which is just the circumference of a circle of radius r, which is 2 pi r. So we will assume that Q and R are given. Therefore, lambda is known, and that the coordinate z of point P is given, although it's arbitrary. Again, our job is to find the electric field vector E arrow at point P on the z-axis, which is perpendicular to the plane of the ring and through its center, as our picture shows. Now here's a very important point that I've really already mentioned. For the point P, like we've shown right here, we cannot assume the ring is a particle. Particle is, tiny. The ring is not tiny. Now, it's true that if you take that point P I've shown on the z-axis and take it far, far away up on the z-axis, well, then that ring starts to look like a point particle, if you're very far away. But we're not talking about that now. Point P is arbitrary, could be quite close to the ring. Very close, in fact. In such a case, you cannot treat the ring as a particle. So if your inclination is to say, well, we already have a formula for calculating electric field. It's Q over 4 pi epsilon 0 r squared. No, unfortunately, we can't do that, because that's the formula for the electric field of a particle. We cannot treat the ring as a particle. So, can't do that. However, the clever aspect of calculus is going to enable me to use that formula I just erased in a certain way. And I'm going to show you that now. Let me tell you the plan of attack. How are we going to do this calculation? For getting the electric field at that point P, distance z from the center of the ring, when we can't treat the ring itself as a particle. Here is the series of steps or ideas. Ready? Plan of attack. First, imagine that the ring consists of an infinite number of infinitesimal is code for tiny, pieces. And each piece has some charge that we're going to call, look carefully, dq. Every piece has the same amount because every piece is tiny and all the pieces are equivalent and the charge is spread out uniformly around the ring, but it's a tiny amount of charge, dq, right? dq means an infinitesimal amount of charge. Now, we get to treat each of these pieces, as a point particle because it's so small, okay? That's really important. Treat each piece as a point particle. It takes an infinite number of those pieces to make up the total ring, but any one piece can be treated as a particle. Next, we'll find the electric field contribution at point P from each piece. And I'm going to label the contribution from any tiny piece with the notation DE arrow. Again, note that. It means a tiny electric field contribution at point P from one of the tiny pieces of charge, dq. And we'll be drawing more pictures, so you'll see. And there's one more step. We will then use what's called the principle of superposition. That just means add. We will add up all the contributions from all the pieces of the ring to get the net electric field, which we will then just label E arrow at point P. Please note this is vector addition, not scalar addition. And it is that net electric field at point P that is the physically real electric field that you would measure. All right, so let's start that process. That's just the plan. We got to go through the steps. Here we go. First step, imagine the ring consists of an infinite number of infinitesimal pieces, each of charge dq. Treat each piece as a particle. Here we go. There's the ring. See it again? It's been drawn. Slightly different perspective, but that's it. You can see little plus signs drawn around it, okay, to represent the smeared out uniformly positive charge, okay? And one little bit's been highlighted in a kind of a pink color. That's a little piece. It's got charge dq, okay? And it's got a little arc length ds, and of course it's at a radius, big R, okay? That's the highlighted piece. Of course, there's an infinite number of those around. We just picked one arbitrarily. Here's the first question. What is the charge dq of this tiny highlighted piece that has arc length ds? That's going to be symbolic. There's not a number here. How much charge dq does that little piece have? Here's the key thing to remember. This ring has a linear charge density lambda. You can think of that as the charge per unit length in units of Coulomb per meter. And that's a property of this ring. So I multiply the charge per unit length of the ring by the length of that little piece, which is that little arc length ds. Okay? That's the length of the highlighted piece. So that would be in meters. Note then that when you multiply the charge per unit length lambda with the length ds, look at what happens to the units. Coulomb per meter times meter, you're just left with coulombs, which is what a charge unit must be. Okay? All right. So we've got a little bit of charge on that highlighted element of the ring, and that amount of charge is lambda ds. That's how we're going to think about it, and it's positive because the ring's positive. Now my question is, I'll draw a little bit of the picture here. What's the contribution to the electric field at that point P up there from just this little piece? I'm going to draw a little straight line from that highlighted piece, little dotted line, to point P to help me visualize. That's a straight line from the highlighted piece to point P. What's the electric field at point P from that little highlighted piece, ds? That's the next question. Again, it's going to be a symbolic expression, no numbers. All right, here's the next picture. Now let's be really clear as we can about this. Then you can see they've drawn in the straight line from the charge element out to point P, and they've said that length, that distance, is little r. All right? The radius of the ring, big R. The distance from the center of the ring straight up the z-axis to point P is a distance z. Make sure all those distances are clear. And we've labeled an angle up here because we've got a little right triangle up there, little acute angle up there, theta. That's just geometry. Now let me talk about that field arrow that you see there. All right, see it's labeled DE. It's anchored at point P because that's where it is. That's where the field is. But it's just from the little highlighted piece. And we have to be clear how they got that direction. It's right along that black line of distance r, but pointing away from the highlighted piece. Do you see that? Okay. Right along that black line of distance r, but directed away from the highlighted piece because the ring is assumed to have positive charge. We're saying, let's assume it's a positively charged ring. So that the DE there has two components. One component along Z and one component that's perpendicular to Z. I'll sketch them here, but you'll see them again in a minute. There's the component along Z, and then straight over for a component perpendicular to Z. And here's an important point. I just made a component triangle, didn't I? And that little acute angle down there, right down there, is the same theta that I had in the RZ big R triangle. All right, so now the question is, what is the magnitude dE of the electric field contribution from this one tiny piece? That's what I want us to talk about next. What is the magnitude of that vector quantity right there? Key thing, treat the tiny piece as a particle. Boy, is that an important point. Now, do you see why it's okay? I was just going on and on a few minutes ago about why you can't treat the ring as a particle. You see why what I'm doing here is not the same? I'm looking at that one little highlighted piece. And it's so tiny in size, by golly, that's a particle. Well, then we know the formula for the electric field of a particle, no matter how small. Take the charge of it over 4 pi epsilon 0 distance squared. Straight line distance from the charge to where you are. We are at point P. Okay, so dE magnitude for that little piece is, whoops, the charge of that little piece, dQ over 4 pi epsilon 0 little r squared is the distance from that little piece to point P. Okay? All right, now I got a couple of notes to write here. First, what's the amount of charge of that little piece, dQ? We just said it's the charge per unit length lambda of the ring times the arc length ds of that little piece. That's important to remember. Next, what is the distance little r from that charge piece to point P? It's convenient to use the Pythagorean theorem here and express little r in terms of big R and Z. Why? Because no matter what little piece of the ring you pick, big R and Z are the same. So little r then is, from Pythagoras, square root of big R squared plus Z squared. And these two quantities right here, both dQ and little r, we now see are the same for every piece of the ring. That's really helpful to note in this case, because we've got a lot of symmetry with something shaped like a circle. And we want to take advantage of that. All right, now that's the magnitude. Let me say a word about the direction of dE, because that's the dE is a dE arrow with a direction as well as a magnitude. The direction of dE is as the picture shows, along a straight line away from the piece that we are looking at, making an angle theta with the z-axis. Does that make sense? That's the direction of dE. All right, now we got to do similar thinking for every piece of the ring. Right? There's an infinite number of little pieces. We've only highlighted one arbitrarily chosen one. Figured out a formula for dE magnitude and talked about the direction in terms of an angle theta that our diagram shows. What if we pick other pieces of the ring and think about their dEs? Because we're going to have to take all these dE vectors and add them up to get the total. And sometimes the charge distribution has a lot of symmetry with it, and that can help you simplify adding up all the dEs. And a circular ring, circular shape, a ring, definitely has a lot of symmetry. In fact, what if I were to pick in addition to the highlighted piece of ring you see right there, the piece of ring that is exactly diametrically opposite to that one. Go right through, right along the diameter, through the center, to this other opposite side, and highlight that diametrically opposed piece, dq. Okay? I contend that it will produce an electric field that will point kind of up and to the left. I'll sketch it here. Like that. Okay? That's up and to the left compared to the DE from the first piece. That's up and to the right. And so what I want to show you in the next picture is those two DEs together. One from our original little piece of ring and the other DE from the diametrically opposite piece of the ring. Because that's the symmetric partner to our first piece. Because we want to use symmetry to help us figure out the direction of the total electric field. All right, that's what we're doing now. We're using symmetry of the charge geometry to deduce the direction of the net electric field at point P. So now I've kind of simplified the drawing a little bit to try to help you focus on the important part. I didn't even draw the ring right now. I just drew the point P, where we're finding the field, on the z-axis. There's the DE from the original piece of the ring. The DE makes an angle theta with the z-axis, so that the DE has a component perpendicular to the z-axis, and it has a component along the z-axis. And then here's the DE from that diametrically opposed piece of the ring. And it makes the same angle theta, but on the other side of the z-axis. And so it has a component perpendicular to z, that would be this one, and a component along z, that would be that one. And the key point is that that component that's perpendicular to z and that component cancel. Right? These components cancel. Ta-da! Right? Don't worry about them then. It's only these components that survive along the z direction. Right? So only z components, this is the key point. Only z component of each DE from each piece contributes to the net electric field at P. So let's write down what that would be like, that z component. Notice how I'm going to denote it. DEZ. Well, just look at the right triangle and remember all you know about vectors and components. Right? I want the z component. I see the angle theta. The hypotenuse is the DE. I need hypotenuse times cosine theta. Right? The hypotenuse is the entire DE. So there it is, DE magnitude. That's the hypotenuse. And then I multiply that by cosine theta. And that's the key component for each little piece that contributes to the field at point P. Hopefully that's clear. Now I have one more thing to do about that cosine theta. One more thing to say about it. What can we say about cosine theta? This picture right here that I've got, not helpful for finding cosine theta. Let's go back to the original picture, or actually what I'm going to do, now that I think about this, is I'm just going to add to this picture. Let's try that. Let me take the straight line distance from point P down this way, to that little highlighted piece that was right there. Okay? That perpendicular distance there is big R, and then that distance right up along there to point P is what we're calling Z. That's little r. And this angle right here is theta. Okay? Because this is the same theta here as up there from geometry. Okay? And so I'm going to look at the bigger triangle below that have distances. And just from that, note that cosine theta, let's see, adjacent over hypotenuse, would be Z over little r. Okay? The bigger triangle, which involves distances, is easier to work with. So let's put all these pieces together and get a symbolic expression for the DEZ of any one piece. It is the magnitude of the DE from any one piece times cosine theta, which is Z over R. And now let's substitute the expression for the magnitude of DE. Where's that coming from? Right here. DE is dq over 4 pi epsilon 0 r squared. Let's put that in. Okay, so for the DE magnitude, dq over 4 pi epsilon 0 little r squared. And from the cosine theta, we have a factor of Z over little r. And then just simplify that. In the numerator, write it like this. Z times dq. And in the denominator, 4 pi epsilon 0 little r cubed. And we've made that about as simple as we can. That's a symbolic expression for the Z component of the electric field from one little piece of the ring. Doesn't matter which one you think about, they're all equivalent. You need this distance Z times the amount of charge of the piece, dq, over 4 pi epsilon 0 times that distance cubed to get the Z component of dE. All right, now there's one more big step. You use this fancy concept called the principle of superposition, and that really just means add up all the components DEZ from all the pieces. The result of that sum will be an integral, and the answer to that integral will be the net electric field at point P. So let's do that. We are now calculating the total field, E, by summing all the infinitesimal DEZs. Right? So you got that expression right there for the DEZs. We're adding them up, all the DEZs from all the little pieces of the ring. Note that adding up an infinite number of infinitesimals is integration. That's why I used the integral symbol. So now I just substitute the expression for DEZ that I just wrote. Z dq over 4 pi epsilon 0 little r cubed. All right, now, the next trick that takes a little getting used to is figuring out, as I do this integral, what quantities inside the integral, the integrand, are not changing as I do the integral, are constants, and can be treated as constants, and what things are changing. All right, so let's think about this. First of all, for the dq, we already had an expression for that, I'll remind you. It's the charge per unit length lambda times the little arc length ds, and that's the same for every piece. Because every piece has the same lambda, and it's the same length. We're making all these little pieces identical. So this is z times lambda times the length ds of any one of the pieces over 4 pi epsilon 0. Now for the little r, look at this picture down here. Little r is that hypotenuse in that distance triangle down there. I better write it in terms of z and big R, because those are given to me as stated symbols. Well, Pythagoras just tells me, as you know, that little r is the square root, in this case, of big R squared plus z squared. Let's put that in. Now it's little r cubed downstairs, isn't it? Be careful. So that means this is big R squared plus Z squared, note, to the 3 halves power. Because the little r expression that I have right up here is big R squared plus Z squared all to the 1/2. And it's little r cubed there. Now, as you imagine working your way around the ring, you take each successive ring one after the other, and you ask, as I go from ring to ring, which symbols in this integram represent things that are changing, and which symbols are things that are constant. And if they're multiplicative constants, they can come out front of the integral. But you can never bring the d blob out front, the tiny infinitesimal. You can never bring that out front of an integral. All right, so note, as you imagine going around the circumference of the ring, little piece by little piece, the z is the same for every piece. It's the distance from the center up to point P. The lambda is the same for every piece. Of course, 4 pi epsilon 0 is all constants. The big R is the same for every piece. And then there's that z again. So look at that. All those things I've highlighted in yellow are constants as far as the integral is concerned and can be brought out front. So you're left with a z times lambda upstairs and a 4 pi epsilon 0 times big R squared plus z squared to the 3 halves. And I'm just left with an integral ds. You can never bring the d blob out front, in this case ds, never. But in this case, everything else. Now, is every problem with a continuous charge distribution going to be that simple? No. Circles have a lot of symmetry, and it turns out to make this integral very easy. Now, the next thing that people struggle with is how to think about this right here. And my point to that is, don't overthink it. Don't overcomplicate it. At the most basic level to a physicist, what does that integral mean? It means add up the little arc lengths of all the little pieces as you go around the ring. Won't that be just the total circumference of the ring when you're done? It will. So don't overthink that in this case. That's what that says to do. Just add up all the little lengths, ds, of all the little pieces going around once. That'll be the total circumference of the ring. Then remember your basic geometry. That's 2 times pi times the radius, big R, of the ring. Don't put little r. That's not the radius of the ring. Right? Every symbol has to have meaning to us here. So look at the final answer for E. Z times lambda times 2 pi big R over 4 pi epsilon 0 times big R squared plus Z squared all to the 3 halves. I know it might look weird, but that's what we get. Now, there is one more thing to note. Right there. Actually, we can identify what that means. Take the charge per unit length lambda, valid at any piece of ring, multiply that by the total distance around the ring. What do you think that would be? What does that mean physically? Did you say that that's just the total charge of the whole ring, which we were told to call Q? Yes, take the charge per unit length times the entire length around. That's what 2 pi big R is. That's the total charge Q. So your answer for the electric field up there at the point P is Z times Q over 4 pi epsilon 0 times R squared plus Z squared to the 3 halves. Wow. Okay? And that is on that perpendicular axis of a uniformly charged ring. The ring has total charge Q, has radius big R, and the point you're at is a distance z up from the center. So then here's the result in a picture with some equations. Okay, there's a picture of the ring again. It centers at the origin. It's in the xy plane. It's got a radius big R. The point P is up here on the z-axis, distance z from the center, total charge Q. Here's the formula for the magnitude of the ring, because this answer will actually work written this way if the ring has positive charge, like I was assuming, or negative charge, as long as the charge total amount is magnitude Q and is spread out uniformly around the circumference. So here we go. Here's the formula for the magnitude. It's on the perpendicular central axis above or below. Wow, or below. E magnitude equals Q magnitude times Z magnitude over 4 pi epsilon 0 times Z squared plus R squared to the 3/2. So it will also work, this formula, if the point Z is below. Just use the absolute value of Z there in the numerator. So there's actually a good bit of information in this answer. Now I've got the formula for getting the magnitude of the field on the z-axis. How about the direction? That's important too. Here's where I do need to keep track of whether it's positively charged ring or negatively charged ring. If it's a positively charged ring, the field points perpendicularly away from the ring. Let me draw it. So up here, if it's a positively charged ring, the field above points up, like that. The field below, by the way, would point down. That's away from the ring. If it's a negatively charged ring, however, the field points perpendicularly toward the ring. Let me draw that. Put in the z-axis again. Now imagine the ring is negatively charged. Then the electric field at point P points towards the ring because it's negatively charged. This formula that we've worked pretty hard to get, we want to get the most out of it that we can be used for either a positively charged or a negatively charged ring, and at a point on the z-axis above the ring or below, if you use the magnitude and direction as discussed here. Let me just mention one more thing about this answer before I finish up this video. The nice thing about this that we worked really hard to get and we want to get the most out of this answer is that we can use it to get a limiting answer. What if the point P is actually very far away from the ring? Okay, so we call that the far field or the distant field, okay? If P is very far from the ring, what does that mean? It means Z, let's just think of it being above, the point P being above, is much, much bigger than the only other distance that's important, which is the radius big R of the ring. If the distance Z is much, much larger than the radius of the ring, little r, it should start to look like a particle. Or ring acts like a particle. And the formula for the field of a particle is Q over 4 pi epsilon 0 distance squared. In this case, the distance would be z. So this answer should reduce to that in the far limit. Note the magnitude of this field formula here looks pretty complicated if you're at a point near the ring. But how does it simplify if point P is far from the ring? Well, when you've got a certain limiting situation, like one distance is much larger than another, z is much, much larger than big R, the first thing to try is the most drastic simplification you can to see if it gives you something that isn't zero. And the most drastic simplification we can do when z is much, much bigger than big R is to go down here in this denominator where there's a z squared plus big R squared and drop the big R squared. All right, what does the E become in that case? Technically, it's an approximation. Magnitude Q, let's just assume the Z is above, so Z is positive, times Z, that's the numerator, 4 pi epsilon 0. Okay, now I had Z squared plus R squared all to the 3 halves. That's now just Z squared to the 3 halves, but that's Z cubed. But I have a Z upstairs and a Z cubed downstairs, so that simplifies to magnitude Q over 4 pi epsilon 0 z squared, just as if the ring were actually a particle with all its charge right there at its center. That's what it starts to behave like if the point P is far away. But that should seem reasonable, and that's what comes out of the math. Right? But that's just a special limiting case. I just want to show you that that weird-looking answer that we got becomes something more familiar in the distant limit. All right, now, here's another idea before I leave you with the class engagement exercise. Some measures of electric charge. This is a table from section 4 in your book. All right, ways to think about charge being distributed. One way is if it's just, if it's just a particle. That's what this is. If it's just a particle, then we would say it's Q and the unit is Coulomb. What if it's what's called a linear charge density? That's something that's shaped like it's basically one-dimensional, like a line, like this pencil, okay? So now I'm talking about, just to be clear, I'm talking about this case, talking about shapes like this, a line like that, like this pencil. Or, I'll give you a perspective view, a circular ring, all right? Or a part of a circular ring. There's also that, which we need to be able to deal with. Those are all linear charge distributions with the charge spread out along a length. And then we talk about the linear charge density, symbol lambda, and SI unit, Coulomb per meter. And that's what we dealt with when we studied the ring just a moment ago. But we'll also come across a situation where we have what's called a surface charge density. That might be, for example, instead of a ring, like I just drew, come down here, but how about a filled-in disk, like a plate, okay? Not hollow or empty inside, but all filled in material, like a plate or a disk. And charge is spread out over that. Now that's a surface. So we call that a surface charge density. Or we might have a surface shaped like a square with charge spread out all over it, okay? So in that case, we have a charge per unit area, or a surface charge density. And that is a different symbol for that. Greek letter sigma. That's a lowercase sigma. And it has SI unit of Coulomb per meter squared. Okay? So, if it's a line distribution, you have a linear charge density, lambda, in coulombs per meter. If it's a surface charge distribution, then you have a surface charge density, sigma, in Coulomb per meter squared. And then thirdly, you could have charge smeared out throughout an entire volume. And that starts to get a little bit harder to draw, but that would be something, for example, shaped like a solid sphere. Let me try to denote that like so, right? A sphere with material all throughout it. And you've got charge in that material. So you've got charge spread out throughout a volume. Or maybe something shaped like a cylinder. okay, with charge smeared out throughout its volume. Okay, there you've got charge per unit volume, or volume charge density. There the symbol is the Greek lowercase symbol rho, not p. Now, yes, we used rho already for mass density. Mass per unit volume, right? Kilogram per meter cubed. Here, it's same symbol for volume charge density. Charge per unit volume in unit of coulombs per meter cubed. So watch out, rho can mean volume charge density or volume mass density. Coulomb per meter cubed or kilogram per meter cubed. Which it means is all on context, what's happening. Okay? So we want to get used to those different kinds of charge densities. Linear charge density, surface charge density, and volume charge density. Okay, last thing for today, for now, is a class engagement question on Blackboard. And it's going to deal with a linear charge distribution over charge spread out over a portion of a ring, okay, of a complete ring. It's still ring shape, it's just not a complete ring. All right, so the question A for this picture. What is the magnitude of the electric field at the center of a uniformly charged circular ring with total charge Q and radius R? At the very center, in the xy plane, you see that point P right there? Right there, okay? Now the picture here shows the charge is negative capital Q. So I guess we ought to make it the same here, okay? But it's got a total charge negative Q that is smeared out uniformly along this rod, which you can see is symmetric about the x-axis with 60 degrees above and 60 degrees below. And we want to know the magnitude of the total electric field E at that central point. Oh, you want to, shoot, I beg your pardon. I said that wrong. I said that wrong, so I apologize for that. I was looking at the picture and I should not have been for part A. Let me try to say it again for part A. What is the magnitude of the electric field at the center of a uniformly charged circular ring with total charge Q and radius R? Total, just an actual ring, full-blown ring, like that, okay? And we want to know the magnitude of the electric field, total electric field, right at the very center. Hint, you can use the answer we just derived. Just got to apply it to the point I just marked with the red X. Okay? Hopefully that's clear now. Okay. Now I go to part B, and that's where this picture comes in, okay? All right. Here's part B. Based on symmetry, you can deduce the direction of the net electric field E arrow created by what we'll call this here circular arc with total charge distributed along its length, and that total charge is negative AQ. Okay? What is the direction of the net electric field at the point P, right there, from that arc? Again, the x-axis goes through the middle, so you got 60 degrees above and 60 degrees below. You've got total charge negative capital Q smeared out along this arc. What's the direction of the net electric field E at the point P? Okay, so two different things. Part A is about a circular ring. Part B is about a circular arc. And those answers you put on Blackboard. And of course, we'll be applying this in our class time as well. That's all for this video.